Ancient people could predict eclipses without any technology. This video reveals how civilizations from Babylon to the Maya mastered the skies using only their eyes and intellect. You will learn the forgotten methods that let them forecast cosmic events with stunning precision, a skill that shaped empires and religions. How did they encode eclipse cycles into myths and stone monuments? And why was this knowledge so powerful? What does their success tell us about human observation itself? The sudden disappearance of the sun was not a scientific event. It was a moment of pure cosmic terror. For ancient cultures, the world depended on the sun's daily journey. When it vanished in the middle of the day, plunging the world into an eerie twilight, it shattered their reality. This was a dragon swallowing the sun, a god expressing wrath, or the precarious balance of the universe tipping into chaos. The same dread applied to a lunar eclipse, where the familiar face of the moon would slowly be consumed by a deep, bloody shadow. These events were divine omens, and the ability to foresee them was the ultimate power. It meant you could commune with the gods, calm the people, and prove your authority. This is why the earliest astronomers, the true pioneers of prediction, dedicated their lives to the sky. They began with the most fundamental tool, patient observation. They noticed that while an eclipse felt like a random, terrifying attack, it did not strike randomly. There was a pattern, a rhythm to the celestial violence. They saw that a certain number of full moons or new moons would pass before the shadow fell again. This was the first crack in the code, the realization that eclipses were part of a vast, repeating cosmic clock. To track this clock, they used what they had. They carved notches on bones, tied knots in cords, or built massive stone circles that acted as giant calendars. An elder might pass down a story, a song that held the memory of past eclipses and the warning for future ones. They were building a database not with computers but with memory and stone. They learned the basic types. A solar eclipse occurs when the moon passes directly between the Earth and the sun, casting its shadow upon us. A lunar eclipse happens when the Earth moves directly between the sun and the moon, casting its own shadow across the lunar surface. Knowing which was which and when each might strike became a matter of survival. It allowed a priest to announce a coming eclipse not as a surprise attack, but as a scheduled and therefore controllable celestial event. This foundational knowledge, carved into the landscape and woven into stories, set the stage for a discovery so precise it would echo for thousands of years. That lone watcher on the plateau possessed no instruments, only a profound and intimate knowledge of the night sky. He would see the moon return to the same group of stars again and again, its path a predictable loop against the backdrop of the cosmos. Over years and then over generations, these patient observers noticed something extraordinary. An eclipse did not happen just once and then vanish forever. After a certain number of lunar cycles, a nearly identical eclipse would occur. The most famous of these repeating patterns is the Saros cycle. It is a period of approximately 18 years and 11 days. After this time, the sun, the earth, and the moon return to almost the exact same geometric alignment, and a similar eclipse is seen from our planet. They did not calculate this with equations. They felt it in their bones, seeing the rhythm play out across a lifetime. One elder would teach a younger apprentice the sacred count, the number of moons to wait after a great darkness falls. This knowledge was encoded in stories, in songs, and in simple physical tallies like notches on a bone or knots on a string. Each mark represented a moon that had passed, a step closer to the next celestial event. This was a legacy written in time itself, a generational project that turned the terrifying unknown into a predictable, manageable phenomenon. The true genius was not in complex math, but in this relentless collective memory. They were building a clock out of human experience, one observation at a time. But these patterns were not just kept in memory, they were carved into the very landscape, transforming entire sites into permanent celestial calendars. The rhythm of the Saros cycle was not just remembered, it was set in stone. Across the globe, ancient cultures engineered their landscape into a permanent astronomical instrument. They built monuments that turned the abstract passage of time into a physical, visible event. Think of a place like Stonehenge, with its massive sarsen stones arranged in a perfect circle. Those towering pillars are not randomly placed. Specific alignments between the stones frame the exact spot on the horizon where the sun rises on the summer solstice. But their purpose went beyond marking the longest day of the year. These structures also tracked the more complex movements of the moon, pinpointing the dangerous periods when an eclipse could occur. This was architecture as a predictive machine, built without metal tools, yet calibrated with stunning accuracy. The builders were not just stacking rocks, they were encoding celestial knowledge into the very fabric of their world. A temple doorway might be positioned so that a sliver of light from the setting sun would strike a single carved altar only once a year on the equinox. Or a narrow window in a pyramid would allow the light of the full moon to illuminate a hidden chamber only during a specific lunar standstill, a key event in the eclipse cycle. For the priests who understood these alignments, the building itself spoke. They could walk through a corridor and see a beam of light falling in a certain way, a silent alarm signaling that the celestial conditions were ripe for an eclipse. This was a fusion of art, religion, and profound science. The monument became a stable, unchanging reference point, a way to cross-check the oral traditions and the knot counts, ensuring the prediction was correct. The power to foresee the gods' anger was literally carved into the walls around them. How did different cultures refine this stone-based science, and what secrets did they discover that we are only now beginning to understand? In the heart of ancient Mesopotamia, Babylonian scribes transformed wet clay into a permanent celestial diary. With a stylus, they pressed wedge-shaped marks, a script we call cuneiform, recording every significant event in the sky. These were not just casual observations, they were state-sponsored intelligence reports. A lunar eclipse was a direct message from the gods, an omen foretelling the fate of the king and the stability of the entire kingdom. The court astronomers had a vital duty to watch for these signs and interpret their divine meaning. Their survival depended on their accuracy. Over centuries, this relentless data collection revealed a powerful truth. They formalized the pattern we know as the Saros cycle, documenting that eclipses recur in families every 18 years and 11 days. This was not a vague prediction, it was a precise, repeatable forecast. They could warn the palace that a celestial event was due, allowing the ruler to perform rituals, prepare the army, or control public sentiment, turning a potential crisis into a demonstration of royal power. Their genius was in the accumulation of data. They did not have a theory of gravity, but they had tablets and tablets of records, a mountain of empirical evidence that revealed the clockwork of the cosmos. This meticulous Babylonian legacy, written in fired clay, became the unshakable foundation for all the astronomy that followed. It proved that the secret to predicting the heavens was not magic, but the patient, relentless work of recording what you see. From the banks of the Euphrates, this practice of careful observation would travel, influencing cultures across the globe, including the sun worshippers of the Nile. For the sun worshippers of Egypt, an eclipse was a moment of profound cosmic danger. Their entire world, from the harvest to the flooding of the Nile, depended on the sun god Ra's daily journey across the sky. When the sun began to vanish, it was not a celestial calculation, it was a mythic battle unfolding before their eyes. They saw it as the serpent god Apep, the embodiment of chaos, attacking Ra's solar bark. The sky itself was a theater for this divine struggle, and the temporary darkness signaled that chaos was winning. The priests had a vital role, not just to predict this event, but to fight it. They would chant, perform rituals, and make offerings to strengthen Ra and ensure his victory, so the light would return to the world. To anticipate these attacks, they turned their greatest monuments into tools. Towering obelisks acted as giant gnomons, their long, sharp shadows sweeping across marked plazas. By tracking the shadow's path and length with meticulous care, priests could detect the subtlest irregularities in the sun's motion, clues that the conditions for an eclipse were nearing. They also noticed a practical pattern. Eclipses seemed to cluster around certain times, often coinciding with the Nile's life-giving flood or the coronation of a new pharaoh. This was not a random connection. An eclipse during a pharaoh's rise could be interpreted as a powerful omen, a sign of divine favor or a warning from the gods. The Egyptian approach was less about mathematical tables and more about symbolic harmony. Their predictions were interwoven with their mythology, their agriculture, and their political power. By framing an eclipse within a story they could influence through ritual, they transformed a terrifying cosmic anomaly into a manageable part of their world order. This deep connection between the sky and the earth was not unique to the Old World. Far across the ocean, in the dense jungles of the Americas, another civilization was building its own breathtakingly accurate celestial calendar, one carved entirely in stone. Deep in the jungles of Mesoamerica, a Mayan astronomer priest unrolled a codex made of beaten bark paper. The pages were alive with intricate glyphs, a complex script detailing the precise movements of the moon and the sun. This was not mere stargazing, it was high-precision cosmic accounting. The Maya possessed one of the most sophisticated calendar systems ever created, the long count, which allowed them to track vast stretches of time. They viewed eclipses not as random attacks, but as predictable moments of celestial vulnerability when the moon goddess was threatened by a dark force. To protect her and maintain cosmic order, they needed to know exactly when these battles would occur. Their secret lay in identifying specific cycles within their ritual calendar. They tracked the lunar semester, a period of 177 days, which roughly corresponds to 6 lunar months. They also calculated the eclipse half-year, a period of 173 days. By watching for the moments when these cycles aligned, they could pinpoint the dangerous windows where an eclipse was not just possible but probable. This knowledge was power deeply woven into the fabric of their society. A priest who could accurately announce an upcoming eclipse solidified his authority, proving his direct line to the gods. This allowed the ruling class to schedule everything from grand ceremonies to the planting of crops around these potent celestial events. An eclipse prediction was a signal to prepare for a major ritual, a time to make offerings that would ensure the sun or moon emerged victorious from its struggle. Their astronomical prowess was so advanced that they even created correction tables, similar to those used in modern science, to fine-tune their predictions over centuries. They understood that their cycles were not perfect, and they built in adjustments to keep their celestial calendar accurate across generations. This was a civilization that lived and breathed the rhythm of the cosmos, turning the terror of an eclipse into a scheduled, managed part of their world. While the Maya were perfecting their calendars in the Americas on the other side of the world, a completely different empire was building its own formidable tradition of celestial prediction, one where an astronomer's mistake could cost him his life. The stakes for an astronomer in Imperial China could not have been higher. Within the walls of the Astronomical Bureau, a state-sanctioned office that operated for over 2,000 years, officials kept a constant watch on the heavens. Their primary mission was to read the celestial signs and, most critically, to predict eclipses. They saw a solar eclipse as a dragon or a heavenly dog consuming the sun, a direct and terrifying omen that the emperor had lost the mandate of heaven. His rule was no longer in harmony with the cosmos. For the emperor, a missed prediction was not a simple error. It was a political catastrophe that could inspire rebellion and shatter the dynasty's legitimacy. An astronomer who failed to foresee the dragon's shadow could pay for that mistake with his life. This immense pressure fueled an unprecedented tradition of meticulous record-keeping. They did not rely on memory alone. They used ingenious tools like the clepsydra, a sophisticated water clock that measured time with a steady, dripping flow, allowing them to log the exact moments of celestial events. They also perfected the armillary sphere, a complex bronze model of the cosmos with rings representing the paths of the sun, moon, and stars. By tracking these movements against their water clock timings, they amassed a vast archive of data. This long-term observation revealed cycles within cycles. Beyond the basic Saros period, they identified the triple Saros, a longer period of about 54 years and 1 month after which a very similar eclipse would recur. This allowed for even more precise long-range forecasting. The entire operation was a bureaucratic machine dedicated to celestial prediction, a fusion of science and statecraft where the goal was not just to understand the sky, but to control the narrative on Earth. A successfully predicted eclipse was a managed event. The emperor and his court would perform elaborate rituals, gongs would be struck to frighten the dragon away, and order would be ceremoniously restored. The Astronomical Bureau's success demonstrated that the ultimate power lay not in preventing the eclipse, but in announcing it first, turning a cosmic threat into a reaffirmation of imperial authority. This deep, state-sponsored entanglement of astronomy and power was a pattern that emerged across the ancient world, from the deserts of the Middle East to the islands of the Pacific. While Chinese astronomers worked under the threat of imperial execution, a different kind of revolution was brewing on the shores of the Mediterranean. Greek philosophers dared to ask a question that would have been unthinkable in many ancient courts. What if an eclipse was not a sign from an angry god, but simply the result of physical objects moving in space? Thales of Miletus, one of the first of these thinkers, is famously credited with predicting a solar eclipse in the 6th century before the Common Era. He likely used the Saros cycle, knowledge that had traveled from Babylon, but his true legacy was not the prediction itself, it was the radical idea behind it. He proposed that the darkening of the sun was a natural event caused by the moon passing directly in front of it. This was a monumental leap, shifting the explanation from the realm of myth to the domain of geometry and reason. The Greeks began to construct simple physical models of the cosmos. They imagined the Earth, the moon, and the sun as spheres moving in space, and they used geometry to understand their relative sizes and distances. They reasoned that a solar eclipse could only happen during a new moon, when the moon is positioned between the Earth and the sun. Conversely, a lunar eclipse must occur during a full moon, when the Earth casts its shadow upon the lunar surface. This was a powerful, logical framework built on observation, not on appeasing deities. Later figures like Hipparchus refined these ideas with stunning precision. He calculated the varying distances to the moon and the sun, and he even developed a method for predicting which eclipses would be total and which would be partial. The Greek approach was a fundamental shift from asking why the gods were angry to asking how the celestial machinery worked. This intellectual curiosity, this drive to find a rational order in the cosmos, bridged the ancient world and the medieval, paving the way for all of modern astronomy. Yet, this was not the only path to knowledge. At the very same time, in the vast expanse of the Pacific, navigators were developing their own profound understanding of the skies, an understanding written not in clay or on papyrus, but in the stars and the waves themselves. Across the vast Pacific, knowledge traveled not in books but in song. An Aboriginal elder in Australia would point to the dark patches within the Milky Way, not as empty voids, but as the great emu in the sky. Its position and posture throughout the year dictated the seasons, and its celestial dance held warnings. The stories of the Dreamtime, the epic creation era, were not mere myths. They were a living map of the cosmos, encoding the rhythms of eclipses within their narrative flow. An elder teaching the next generation was not just sharing a tale, they were passing down a precise observational database. The moment when the sun and moon briefly united or battled in the sky was a scheduled event within this eternal story, a moment to be anticipated and understood, not feared as a random omen. This was a science of memory woven into the very fabric of culture. In North America, similar wisdom flourished. Certain native tribes observed that a lunar eclipse often coincided with the prominence of specific constellations, like the sweeping tail of Scorpius or the belt of Orion. This was not a mathematical calculation, it was a pattern recognized through generations of patient watching. When that constellation rose to a certain point in the autumn sky, the community knew it was time to be watchful. The shaman would then prepare the people, guiding them through rituals designed to encourage the moon to break free from the shadow that sought to consume it. This knowledge was embodied, performed through dance and ceremony. A dance step might mimic the slow dimming of the moon, and a rhythmic chant might count out the traditional number of days between dangerous periods. The entire community participated in this act of prediction and response, reinforcing their bond with the cosmos. This proves a profound truth. Predicting an eclipse did not require a written language or complex tools. It demanded a deep, symbiotic connection to the environment and a cultural commitment to preserving that connection across countless generations. The accuracy of these oral traditions is not just legend. When we compare the eclipse lore of the Australian Aboriginal peoples with the stories of the Navajo in the American Southwest, we find a remarkable convergence. Separated by an entire ocean, these cultures independently identified the same repetitive cycles in the sky, encoding them into their respective worldviews. This global consensus, emerging from deserts, jungles, and islands, points to a single, inescapable conclusion. The human mind, armed with nothing but patience and a desire to find order, is a powerful instrument of discovery. A wolf in Scandinavia and a demon in India both hunt the sun. Separated by continents and cultures, these civilizations told nearly the same story to explain a solar eclipse. This was not a coincidence. It was the result of independent observers all looking up at the same sky and arriving at the same fundamental truth. The terrifying event in the heavens was not random, it followed a pattern. The evidence for this shared understanding is etched into the historical records they left behind. Babylonian clay tablets, Chinese Imperial archives, and Mayan codices all point to the same celestial rhythm, the Saros cycle. Each of these cultures, working in isolation, identified that eclipses repeat in a family every 18 years and 11 days. They also noticed that these events often clustered around specific seasons, tied to the agricultural calendar or significant religious festivals. This was not the result of one culture teaching another. It was a universal human discovery, a testament to the power of the naked eye and the disciplined mind. When you watch the same sky for generations, certain patterns become undeniable. The real mystery is not that they found these patterns, but that they found them independently across the globe. This points to a profound idea. The cosmos operates on a logic that is accessible to anyone with the patience to look. You do not need advanced mathematics to see that after a certain number of full moons, the shadow will fall again. You just need to pay attention and to remember. This collective, global effort to decode the sky reveals a deep-seated human drive to replace fear with understanding, to transform a cosmic threat into a predictable event. The guardians of this hard-won knowledge were almost always a specialized class, the priests and shamans who held the celestial secrets. Their role was not just to predict, but to perform the rituals that ensured the sun or moon would be reborn. This responsibility gave them immense power, but it also came with a heavy burden. They were the keepers of the calendar, the interpreters of the gods, and the bridge between the human world and the cosmos. The survival of their entire cultural knowledge depended on their ability to accurately pass this information down through the generations, a chain of memory that could not be broken. The Vedic priest chant rises into the night, a desperate plea against the shadow swallowing the moon. He is not just a holy man, he is a cosmic first responder. His entire ritual, from the specific offerings to the precise mantras, is designed to fight the serpent Rahu, to free the moon from its celestial grip. This was the profound dual role of the priest and shaman across the ancient world. They were the celestial interpreters, the only ones who could translate the violent language of the sky into terms their people could understand and survive. Their spiritual authority was directly tied to their observational skills. A shaman who could correctly announce an eclipse was not guessing, he was communicating with the gods. He held the sacred secrets of the cycles, knowledge often guarded so closely that it became a form of power in itself. In Druidic Europe, these secrets were memorized in vast oral poems containing the movements of the stars and the patterns of eclipses. An Inca priest high in the Andes might use a complex set of knotted strings, a quipu, to record the passage of time between celestial events. These were not just calendars, they were mnemonics, memory devices that held the community's entire astronomical knowledge. The ability to read them was a sacred trust. This knowledge was the ultimate tool for maintaining social order. By predicting an eclipse, a priest could frame it not as a random disaster, but as a scheduled divine event. He could prepare the people, lead them in the proper rituals, and then take credit when the sun or moon inevitably returned. This demonstrated clear divine favor, solidifying his authority and the stability of the ruling class. In this world, science and religion were not separate disciplines, they were two sides of the same coin. Understanding the sky was a form of worship, and accurate prediction was the highest prayer. The tools they left behind, from stone circles to carved codices, are not merely artifacts. They are the physical proof of this deep, inseparable bond between the human desire to understand and the need to find meaning in the cosmos. A stone tablet unearthed in Turkey is covered in strange symbols. To modern archaeologists, these markings were a mystery until they were cross-referenced with known celestial events. The symbols perfectly described a total solar eclipse that occurred in the year 763 before the Common Era. This is not an isolated discovery. Physical evidence of ancient eclipse prediction is found all over the world, etched into bone, bronze, and stone. In China, oracle bones from the Shang dynasty bear inscriptions that record eclipses as messages from the heavens, providing precise dates that modern astronomers can verify. Far across the globe, petroglyphs carved into rock faces in the American Southwest may depict the corona of a total solar eclipse, a sight witnessed by the artists thousands of years ago. These artifacts are more than just historical records. They are frozen moments of observation, proof that our ancestors were not just watching the sky, they were diligently logging its behavior. The most stunning example of this ancient engineering is the Antikythera mechanism. Recovered from a shipwreck in the Mediterranean, this complex bronze device is a breathtakingly advanced analog computer. Its intricate system of gears could predict lunar and solar eclipses years in advance, modeling the irregular motions of the moon with a sophistication that would not be seen again for over 1,000 years. It was a portable prediction machine, turning abstract celestial cycles into a tangible, mechanical reality. Even massive monuments served as permanent records. The massive passage tomb at Newgrange in Ireland, older than both Stonehenge and the Egyptian pyramids, is precisely aligned with the winter solstice sunrise. But some researchers believe its deeper passages and chambers may have also tracked the moon's more complex cycles, marking the times when a lunar eclipse was possible. Each of these objects, from the simplest notched bone calendar to the most complex geared mechanism, tells the same story. Our ancestors were not passive victims of celestial events. They were active scientists, using the tools at their disposal to inscribe their understanding of the cosmos into permanent form. They left behind a legacy in metal and rock, a testament to their drive to measure, to record, and to ultimately conquer their fear of the dark. A Mesopotamian astronomer would plant a simple stick in the ground, watching its shadow shorten and lengthen with the passing days. This was the gnomon, one of humanity's first and most powerful scientific instruments. By carefully marking the tip of the shadow's path each day, he could map the sun's journey. The shortest shadow marked the summer solstice, the longest the winter solstice. But more subtly, the precise curve of that daily path revealed the approaching eclipse seasons, the dangerous periods when the sun, earth, and moon could fall into perfect shadow-casting alignment. This was not complex math, it was pure, consistent pattern recognition. In Egypt, the tool of choice was the merkit, a simple plumb line used with a sighting tool. A priest would hold one merk steady, using its weighted string to find a true vertical line, while a colleague sighted a specific star through its V-shaped notch. By tracking the transit of stars across the night sky with this simple device, they could divide the night into hours and calibrate their water clocks, ensuring their celestial observations were perfectly timed. The Chinese perfected the clepsydra, or water clock, into a masterpiece of steady measurement. Water would drip at a constant rate from one reservoir into another, the rising level indicating the passage of time. This allowed them to log the exact moment an eclipse began and ended, creating the precise data needed to identify long-term cycles like the triple Saros. Far across the world, a Mayan astronomer might hold two sticks, crossing them to form a simple sighting device. By aligning the intersection with Venus and the Moon, he could track their converging paths, knowing that when they met in a specific part of the sky, the conditions for an eclipse were near. The sheer ingenuity of these tools lies in their elegant simplicity. They required no advanced geometry, only meticulous observation and a deep trust in the regularity of nature. Innovation was not about complexity, but about finding the most direct path to measure the cosmos. This hands-on approach, relying on physical tools and sensory experience, laid the groundwork for an even more profound leap, one that moved from observation to pure, abstract calculation. The key to this long-term prediction lay in the mastery of celestial cycles. A Greek astronomer would have tracked the moon's phases year after year, and after 19 years, he would witness a remarkable alignment. The phases of the moon returned to fall on the exact same dates of the solar year. This is the Metonic cycle, a near-perfect harmony between the sun and the moon. It became the foundation for lunisolar calendars, ensuring that religious festivals tied to the moon's phases would not drift out of their proper seasons. But for predicting the shadow itself, another cycle was even more critical, the Saros. Imagine an eclipse as a single note in a cosmic song. After a period of 18 years and 11 days, that same note would sound again. This is the Saros cycle. The Sun, Earth, and Moon return to almost the same relative positions, and a nearly identical eclipse occurs. The ancient observers noticed that these eclipses traveled in families, each Saros series beginning with a partial eclipse, building to a sequence of spectacular totals, and then fading away over a span of more than 1,000 years. By simply keeping count of these 18-year intervals, a Babylonian scribe or a Mayan priest could look decades, even centuries, into the future. They could know not just that an eclipse was coming, but what kind of eclipse it would be, and even the general path its shadow would trace across the Earth. Another powerful tool was the Inex cycle, a longer period of 29 years. This cycle effectively resets the Moon's orbit, bringing it back to the same point relative to the Sun. By watching for the moments when the Metonic, Saros, and Inex cycles converged, these ancient astronomers could pinpoint the most dangerous, the most potent eclipse seasons with stunning accuracy. This was not magic, it was the result of recognizing the deep, rhythmic pulse of the cosmos itself. These cycles became the beating heart of timekeeping, from the ziggurats of Babylon to the stone circles of Britain. They transformed the sky from a chaotic display of divine whims into a predictable, mechanical clock. And once you know the clock is predictable, you can build your entire culture around its ticks. The howl of a wolf was not just an animal cry, it was a cosmic warning. For the Norse, the sky was a desperate chase. Two wolves, Skal and Hati, eternally pursued the sun and moon. An eclipse meant one of the beasts had finally caught its prey, a terrifying sign that the final battle of Ragnarok was imminent. This was not a unique fear. Cultures around the world explained the sudden darkness with the same fundamental story, a drama of gods and monsters. In Hindu tradition, the decapitated demon Rahu, his head forever separated from his body, seeks vengeance on the sun and moon for revealing him to the gods. He chases them across the sky, and when he catches and swallows one, an eclipse occurs. But because he has no throat, the celestial body simply falls out and light is restored. These myths did more than just explain a frightening event. They transformed chaos into narrative. A story about a demon swallowing the sun is scary, but it is a story with a known ending. The sun always escapes. This structure provided a profound psychological comfort. It gave people a role to play. The Norse would make as much noise as possible, shouting and banging drums to scare Skal away. Hindus would immerse themselves in sacred rivers, praying for the sun's release. The community came together in a shared, purposeful ritual, actively participating in the salvation of their world. These stories were also ingenious memory devices. The predictable cycle of Rahu's futile swallowing and the sun's inevitable escape perfectly mirrored the actual periodicity of eclipses. An elder teaching this myth was not just passing down a tale, they were encoding the Saros cycle into a vivid, unforgettable image. The story itself became a calendar, a way to remember that after a certain number of seasons, the demon would hunt again. This mythological framework was the ancient world's user manual for the cosmos. It provided both an explanation for why eclipses happened and a set of instructions for what to do when they did. It turned passive terror into active, managed response, proving that the human mind's greatest tool against fear is not just observation, but the stories we tell about what we see. That moment of unexpected darkness was more than a celestial event. It was a psychological earthquake. A solar eclipse in the ancient world triggered a primal, collective fear. The sun was the ultimate source of life, and its sudden, inexplicable disappearance felt like the end of the world. Imagine the rising panic in a village square as the light faded, the air grew cold, and birds fell silent. This was not a quiet awe, it was sheer terror. People would bang pots, scream at the sky, and fire arrows into the air, all in a desperate attempt to fight off the invisible monster swallowing their sun. This raw emotional response created a power vacuum, and into that vacuum stepped the predictors. The priest who knew the eclipse was coming held immense power. He could stand before the terrified crowd and perform a prearranged ritual at the peak of the darkness. He would chant, make a symbolic offering, and just as the sun began to return, he would raise his arms in triumph. To the people, he had not predicted the event, he had caused the sun to return. He had won a battle against the gods of chaos. This was the ultimate tool for social control. A ruler or priest who could seemingly command the cosmos solidified their authority in a way no army ever could. Their power was seen as divinely mandated. This is why prediction methods were so fiercely guarded and preserved. They were not just scientific data, they were the keys to political stability. The knowledge was often kept within elite families or secretive priesthoods, passed from master to apprentice as a sacred trust. The ability to forecast an eclipse allowed the ruling class to transform a moment of societal collapse into a reaffirmation of their own necessity. They turned cosmic chaos into a scheduled demonstration of their divine connection. This deep human need for order, for someone to have the answers in a moment of terror, is what fueled the relentless pursuit of celestial knowledge across millennia. A Maya scribe carefully mixed his ink, knowing the symbols he painted held the future of his civilization. His task was not just to record, he was copying an entire eclipse table from an older, crumbling codex onto fresh bark paper. This was a sacred duty, ensuring that the precise counts and dangerous periods would be known to priests 100 years from now. Across the ancient world, this battle against forgetting was fought on three fronts: through memory, through writing, and through stone itself. In West Africa, griot storytellers did not use paper. They committed epic poems to memory, songs that contained the genealogies of kings intertwined with the celestial events that shaped their reigns. A single line in a multi-part epic might encode the specific season when an eclipse darkened the sky before a great battle, preserving that astronomical data within a compelling narrative. This oral tradition was a living library, passed from one generation to the next in a continuous chain of recitation and listening. In Cambodia, the solution was more permanent. The kings of the Khmer Empire inscribed their history and their cosmology into towering stone stelae. These massive pillars, covered in intricate script, recorded the dates of important celestial events, anchoring them to the reign of a specific god-king. The stone itself was the guarantee that the knowledge would endure beyond a single human lifetime. Perhaps the most ingenious method of all was architectural. A temple was not just a place of worship, it was a permanent teaching tool. The sprawling temple of Karnak in Egypt is a perfect example. Its main axis is precisely aligned so that the rays of the winter solstice sun would shine directly down its central corridor, illuminating the inner sanctum. This alignment did more than mark the shortest day, it served as a fixed celestial reference point. By understanding the sun's position at the solstices, priests could then calculate the more complex lunar cycles that signaled the approach of an eclipse season. The building itself taught each new generation of priests how to read the sky. This knowledge was power, and it was often guarded with intense secrecy. Training was rigorous and reserved for a select few, usually within elite families or a closed priesthood. An apprentice would spend years memorizing cycles, learning to use sighting tools, and being taught the secret meanings behind the public myths. This protected the authority of the ruling class and ensured the information was not corrupted or lost. This multi-generational project, spanning continents and cultures, reveals a universal truth. The drive to preserve hard-won knowledge, to build a legacy of understanding that could outlast any single person, is what truly allowed humanity to conquer its fear of the dark. Two armies stood frozen on a battlefield in Anatolia. The Lydians and the Medes were locked in a brutal 5-year war, their spears raised and shields braced for the final charge. Then, without warning, the sky began to die. The sun, the very source of light and life, was being devoured by a creeping black disk. Day turned to an eerie, premature twilight. The soldiers' battle cries faltered, replaced by shouts of pure terror. They dropped their weapons, believing the gods had abandoned them, but one man had foreseen this celestial intervention. The Greek philosopher Thales of Miletus had reportedly predicted this very event, the solar eclipse of 585 before the Common Era. The shock of the darkness was so profound that the warring kings immediately laid down their arms and negotiated a peace treaty, sealed by a double royal marriage. How did Thales accomplish this? He almost certainly did not possess a complex theory of planetary motion. The key likely came from the East, from the vast astronomical archives of the Babylonians. They had long ago documented the Saros cycle, the 18-year and 11-day period after which eclipses repeat. Thales, living on the coast of Anatolia, was at a cultural crossroads. This knowledge, carefully guarded by Babylonian priest astronomers, could have traveled along trade routes, reaching a mind ready to apply it in a new way. Thales saw the pattern not as a divine omen for a king, but as a predictable, natural occurrence. His genius was in its application. He used this borrowed celestial clockwork to make a very public, verifiable prediction far from home. The result was not just a stopped battle, it was a seismic shift in human thought. On that day, the darkness did not signal the anger of the gods, it illuminated the power of human reason. A philosopher, not a priest, had read the sky. This event marks a pivotal moment where eclipse prediction began its slow transformation from a secretive, magical art into a demonstrable, rational science. It proved that forecasting the heavens could be a tool for earthly peace, a way to wield knowledge that was more powerful than any sword. The execution of court astronomers was a grim reality in ancient China. The Book of Documents records an emperor's brutal response to a missed prediction, a failure seen not as a scientific error but as a direct threat to the state. The emperor could not tolerate such incompetence, for an unpredicted eclipse shattered the illusion of his divine mandate. This was the ultimate pressure that drove innovation, where a single mistake could end a career and a life. On the other side of the world, a predicted eclipse could end a war. The solar eclipse of 585 before the Common Era, foretold by Thales of Miletus, famously halted the battle between the Lydians and the Medes. As daylight vanished on the battlefield, the warring soldiers interpreted the event as a divine command for peace. They immediately laid down their weapons, and the kings negotiated a treaty. This was not a story about one man's genius, but about the power of a known celestial schedule to alter human destiny. In Mesopotamia, the stakes were equally high. An eclipse prediction was a tool of political validation. A king whose astronomers could accurately forecast an event could frame it as a scheduled communication from the gods, a moment he had prepared for with ritual and spectacle. This transformed a potential crisis into a public relations triumph, reinforcing his authority. But if a rival court predicted an eclipse that the king's own seers had missed, it was a devastating blow, proof that the gods favored another. The consequences of these predictions rippled through culture, shaping the narratives we still read today. Some scholars suggest that the legendary darkness described in the Bible, the plague of darkness in Egypt, could be a cultural memory of a predicted and terrifying solar eclipse, an event so profound it was woven into the foundation of a religion. Each of these historical moments, from the silenced astronomers in China to the battlefield piece in Anatolia, reveals the immense real-world stakes. The ability to read the sky was not an abstract science, it was the key to power, peace, and survival. This relentless pressure to be right, generation after generation, is what forced the continuous refinement of their methods, pushing ancient astronomy to its absolute limits. Inside a quiet European monastery, a monk carefully turned the parchment pages of an ancient text. He was not reading scripture, but consulting the celestial calculations of Claudius Ptolemy, an astronomer from the 2nd century. His goal was to predict the next lunar eclipse, a critical date for fixing the movable feasts of the Christian calendar, especially Easter. This was the fragile thread of continuity, the means by which the hard-won knowledge of the Babylonians and Greeks survived the collapse of empires. That thread was strengthened immeasurably during the Islamic Golden Age. In observatories from Baghdad to Damascus, scholars like al-Battani meticulously observed the heavens, correcting the star catalogues of Ptolemy and refining the values for key cycles like the Saros. They produced new, more accurate astronomical tables, the Zij, which became the standard reference for centuries. These texts, translated into Latin, flowed into the intellectual centers of a reawakening Europe. Even as the Renaissance dawned and mathematics began to offer new tools, the foundational methods persisted. Astronomers still relied heavily on the Saros cycle and the long observational records passed down from antiquity. They were using a clock built by ancient hands, simply checking its time against their own newer observations. This centuries-long chain of preservation and refinement proves the raw power and durability of the original discovery. The patterns etched on Babylonian clay were still yielding accurate predictions over 1,000 years later. Yet for all their brilliance, these ancient methods were not perfect. They contained subtle flaws that could, over time, lead to significant errors. The Saros cycle is not an exact whole number of days, but includes an extra third of a day. This means that each recurring eclipse in a series is visible from a different part of the globe. An astronomer in Babylon might perfectly predict an eclipse that would only be visible over the Pacific Ocean, completely missing his own sky. Furthermore, the cycles they tracked so carefully only pinpointed the possibility of an eclipse, a window of time when the sun, earth, and moon were roughly aligned. They could not always forecast the exact type, duration, or the precise path of totality with modern accuracy. A predicted major eclipse might turn out to be a minor, barely noticeable partial one. These limitations remind us that their genius lay in pattern recognition on a grand scale, not in the precise orbital mechanics we understand today. Their predictions were a brilliant, human-scale map of the cosmos, but the map was not the territory. The Babylonian astrologer's calculations pointed to a certain night. The air was clear, the sky perfect for observation. He waited, his career and possibly his life hanging in the balance, but the moon remained full and bright, untouched by the Earth's shadow. His prediction had failed. This was a common and terrifying reality. The Saros cycle, while brilliant, was an imperfect tool. Its period is not a whole number of days, but includes an extra 8 hours or so. This meant that while the celestial geometry repeated, the visibility of the eclipse shifted westward by roughly 1/3 of the planet with each cycle. An eclipse predicted for Babylon might actually be happening over the Atlantic Ocean, completely invisible to the very people who had forecast it. They were predicting the event itself, not necessarily its appearance in their local sky. This fundamental limitation, born from a lack of global perspective, led to many false alarms. Even when an eclipse did occur, they could misjudge its magnitude. A prediction for a dramatic, total blackout might result in only a slight, barely noticeable dimming of the sun or moon. Their methods identified the dangerous window, the eclipse season, but could not always pinpoint the exact type or intensity with modern precision. The data they relied on was also vulnerable. A year of cloudy skies during a key lunar event could create a gap in their records, breaking the chain of observation. Political pressure introduced another source of error. A king eager for a favorable omen might influence his astronomers to interpret ambiguous signs as a guaranteed eclipse, or a scribe recording past events might fudge a date to make a previous prediction seem more accurate. These were human systems subject to all the flaws of memory, bias, and ambition. These shortcomings are not marks of failure. They are proof that ancient astronomy was a living, evolving practice. It was a science of best estimates, refined over centuries but always operating within the constraints of their world. Their genius lay in how much they achieved with so little, building a cosmic clock that ticked for millennia, even if it occasionally lost a second. This legacy of brilliant observation sets the stage for a final, revealing comparison. How do their methods, forged in patience and stone, stand up against the razor-sharp precision of modern astronomy? A Maya priest's entire prediction rested on a single, repeating calendar cycle, a rhythm he trusted with his life. Today, a NASA engineer sends a command to a satellite orbiting 1,000,000 miles away, verifying the moon's position down to the centimeter. The goal is identical: to foretell the precise moment when light will vanish, but the paths to that knowledge are worlds apart. The ancients were masters of pattern recognition. They observed the cosmic rhythms, identified cycles like the Saros, and built a predictive model based on repetition. They knew an eclipse was due because it had happened before, in a nearly identical way, 18 years and 11 days prior. Their genius was in seeing time as a loop. Modern science, in contrast, sees the solar system as a dynamic system of gravitational forces. We use the laws of orbital mechanics, equations born from the work of Newton and Einstein, that describe not just the repeating patterns, but the underlying reasons for them. We don't just know that an eclipse will happen, we can calculate the exact shape of the moon's shadow, its speed across the Earth's surface, and the duration of totality to a fraction of a second for any location on the planet. This is the difference between observing a clock's hands move and understanding the intricate interplay of gears and springs inside. The ancient method was brilliant, but it was a black box. They knew the output, the eclipse, would occur after a certain input, the cycle count, but they did not have a complete physical model of why. Our modern approach opens that box, revealing the celestial machinery in all its complex, calculable glory. We have replaced the cyclical calendar with a dynamic simulation, running on supercomputers that can project eclipses thousands of years into the future or past. Yet for all our technological supremacy, our predictions still ultimately rest on the same foundation: observation. Our satellites and telescopes are simply extensions of those first naked eye watchers on the plateau, gathering data with infinitely greater precision. This journey from pattern to principle reveals a profound truth about our species. The desire to replace celestial mystery with reliable forecast is a thread connecting the Babylonian scribe to the modern astrophysicist. We are still answering the same primal call: to look into the sky and not only see what is there, but to know what will happen next. This legacy of ancient sky watchers is not just a historical curiosity, it actively shapes how we explore the cosmos today. A stone circle in Scotland stands silent against the moor, its purpose lost for millennia. Modern archaeologists arrive not with ancient songs, but with laptops and astronomical software. By carbon dating charcoal fragments from a nearby ritual pit, they establish the site was active around 1500 years before the Common Era. Then, they input the precise alignments of the stones into a program that can rewind the sky. The simulation reveals a stunning fact. On a specific day over 3,000 years ago, the setting full moon would have risen directly between two key pillars, perfectly framed, just as a total lunar eclipse began. The digital sky confirms what the stones had been proclaiming all along. This is not an isolated case. Researchers now routinely cross-reference ancient monuments and artifacts with computerized celestial models. The results are a powerful vindication of our ancestors. Analysis of Babylonian clay tablets reveals that their eclipse warnings, calculated using the Saros cycle, were often accurate to within just a few hours. A Chinese record of a solar eclipse in 1316 before the Common Era, when checked against modern astronomical retrocalculations, proves to be precisely correct. This validation does more than just honor their intellect. It opens a unique window into the past itself. When an ancient text from the Maya describes the sky darkening during a specific king's coronation, and modern software confirms a total solar eclipse was visible from that very city on that exact date, the event is locked into history. This precise dating helps archaeologists build more accurate timelines for entire civilizations. Beyond chronology, these confirmed eclipses can tell us about Earth's own history. The exact duration and path of a solar eclipse are subtly affected by the planet's rotation. By comparing ancient descriptions of totality with modern models, scientists can detect tiny, cumulative changes in Earth's spin over centuries, data that contributes to our understanding of long-term climate patterns. This rigorous modern testing proves that their empirical methods were not just lucky guesses. They were a robust, effective science built on a foundation of relentless observation and cultural memory. Their legacy of watching the sky is a gift that still informs our world today. A total solar eclipse today sends millions of people outside with special glasses, their faces turned upward in collective wonder. This shared moment of awe is a direct echo of the ancient sky watchers on their plateaus and pyramids. The legacy of their methods is woven into the very fabric of modern science. Johannes Kepler, for instance, used the meticulous records of the ancient astronomer Ptolemy, who himself built upon Babylonian data to formulate his laws of planetary motion. He was standing on the shoulders of giants who worked with nothing but their eyes and their patience. The Saros cycle is not a forgotten relic. It is a fundamental concept taught in introductory astronomy courses, a testament to the enduring power of that 18-year rhythm first discerned millennia ago. Beyond the equations, there is a growing recognition of the profound wisdom held in Indigenous sky lore. The celestial stories of Aboriginal Australians or Native American tribes do more than predict eclipses. They encode intricate ecological knowledge, linking the positions of stars and planets to seasonal changes, animal migrations, and the flowering of plants. This is a holistic science that modern ecology is only beginning to fully appreciate. The true lesson of these ancient achievements is not about the tools they lacked, but about the profound human potential they represent. They teach us that curiosity, coupled with relentless observation and the courage to seek patterns in the chaos, can unlock the secrets of the cosmos. In an age of supercomputers and space telescopes, their legacy is a powerful reminder that the most essential instrument for discovery has always been, and will always be, the human mind. That quest to decode the cosmos, stretching from Babylon to the Maya, reveals something fundamental about us. It shows that scientific discovery is not born from technology, but from a timeless human instinct to find order in the chaos. Those ancient watchers, armed only with their eyes and their intellect, were practicing the very essence of science, patient observation. They proved you do not need a supercomputer to understand the universe. You need curiosity, resilience, and the courage to look up generation after generation. Their legacy is not just a collection of predictions, it is a powerful reminder of our own potential. When you stand beneath the next eclipse, feeling that sudden chill and watching the sky darken in the middle of the day, you are connected to every human who ever gazed upward in wonder and sought to understand. You are part of that unbroken chain of discovery. Thank you for joining this journey into the deep past. If these stories of ancient sky watchers ignited your curiosity, subscribe for more explorations into history's greatest mysteries. We would love to hear your thoughts on this incredible chapter of human achievement in the comments.